Hello, everybody. So I won't talk about data assimilation. I will focus more on a strategy to derive almost automatically stochastic representation of geophysical flow dynamics. So this is a joint work with Werner Bauer and Langue. So I don't need to motivate the fact that there is a very strong, huge interest on the use of stochastic filter. We saw that in the previous talks, and as well as for ensemble methods for weather forecasting, for instance. So, but all these settings, they require either implicitly or explicitly the setting of a stochastic version of the dynamics. So implicitly through the definition of a covariance matrix, or explicitly in the definition of a stochastic dynamics. And it's not obvious how you define such a stochastic dynamics if you want, for example, to preserve conservation properties that you have on the deterministic setting. So there has been several works or several principles that have been proposed in the literature toward that purpose. Some of them are, let's say, ad hoc. They are considering additive or multiplicative perturbation of the parameters of the dynamics. They are based on previous works in the turbulence community, such as the work of Lee or Mason and Thompson, in which they wanted to model the backscattering effect of the energy toward across scales. There have been worked to model reduce order model based on a low fast mode decomposition with some ansatz on the fast modes, mainly a linear ansatz for these fast modes. And I want to describe a different approach based on stochastic transport. So you have seen one example, which is related to the work of Daryl Ohm, and then I will present another one, which is called, oh, okay, does it work? Okay. Okay, which is called modeling under location uncertainty. So I will describe briefly the principle of this setting. So in the same way as in the previous talk, the Lagrangian velocity is decomposed into two components. One smoothing time component, a W, which is the resolved velocity, and a highly oscillating component, which is a random component, model with a Brownian term, which means that the assumption here is that this component is decorrelated in time from this one at the characteristic time scale of this component. This component can be random as well. It's not necessarily deterministic. Okay, the noise is described in the following way. So it's described through an integral operator, which is defined through a symmetric kernel. This kernel is deterministic, and the process is this operator is supposed to be Hilbert-Schmidt in order to have a finite covariance operator. So the covariance operator, you get it straightforwardly from this formula. It implies the multiplication of the two kernels, sigma breve, and one object of interest in stochastic calculus is the diagonal of this covariance matrix. This is the quadratic variation term. This is, okay, the diagonal of the covariance divided by decorrelation time. So this has a dimension of dissipation, okay, of a viscosity. Sorry, it's meter square per second. You can relate this to the turbulent kinetic energy by taking the trace of this tensor A, and then you've got the T key. So to derive the dynamics from this decomposition, we need one tool, which will be the stochastic version of the Reynolds transport theorem. So we will assume that the random field is incompressible. We can do the computation for a compressible random field, but it complexifies a lot the expression, so we will stick to the incompressible version. So the rate of change of a scalar process theta within a volume transported by the stochastic flow can be expressed in the very similar way as in the deterministic setting through the material derivative and the divergence of the advection velocity. This material derivative in the stochastic setting takes this form. It's quite similar to the deterministic setting. You see a partial derivative with respect to time and advection term. There is an additional diffusion term that appears here. And it's nice to talk about the different terms that are appearing there, so which are very useful for turbulence modeling, for instance. You have here a diffusion term, which pictures the mixing of the large scale by the small scale, and it's driven by the variance of the noise. You have an advection of the large scale by the small scale, the random part of the velocity, and you have a correction of the advection, which is the statistical influence of the inhomogeneity of the noise. And so, and this term is indeed very important because it allows us to model the inhomogeneity of the turbulence. So, for instance, it can be seen rigorously as a generalization of the Stokes drift in ocean modeling, and it allows also to model a transitional regime like the buffer zone in boundary layer turbulence. So you can express now, okay, the conservation of a passive scalar, which is the material derivative of this scalar equal to 0. And then you can check that, as in the deterministic setting, you have a conservation of the energy of this scalar. Indeed, okay, this is the Ito bracket that you need to introduce in this computation. And the Ito bracket balances, in fact, the dissipation term that is attached to this derivative. You can, from this, you may decompose also theta in terms of an expectation and variance, and then you will have that you will see that the expectation is dissipating energy, whereas the variance is producing energy, but they are balanced. They are in equilibrium. Okay, so I will with that tool, you can derive all the dynamics model that you want to have. So you start from a stochastic flow with a stochastic version of the Reynolds transport theorem. You get the 3D Navier-Stokes equation, stochastic version of the 3D Navier-Stokes equation, with the usual assumption such as Boussinesq assumption or hydrostatic balance. Then you get the 2D rotating shallow water equation. So you can extend it in a multi-layer context. And if you do some power expansion on a small number, like the Rossby number, then you can get a QG approximation. But then you have, opposite to the deterministic setting, you have to discuss the scale of the noise you have now. So in this context, the scaling of the noise is the following. So we assume that here the noise is of the order of the mean kinetic energy. And so by doing so and discussing all the terms in the of your system, you end up with a QG model in which you have an evolution equation for the potential vorticity, which includes two additional source terms compared to the deterministic case. These two terms are given here and here. There is a finite variation term and a martingale term. And you have also the relation between the string function. This is the usual relation between the string function and the stochastic potential vorticity. The source term that you have here, they allows you to have to conserve the energy, of course, in the absence of dissipation and forcing term. But without these source terms, you won't have this conservation of total energy. So I will discuss now some very simple parameterization of the noise, and we will compare their effects on two different cases. So the first one is the most straightforward. So it's an homogeneous and stationary in time noise. So that's the most straightforward way to set up such a noise. You decompose it on the Fourier basis, and you set the coefficient of this Fourier basis with respect to the spectrum of energy. You set some range for this noise, and that's all. And then you get an homogeneous noise. You can go to a non-stationary noise if you consider instantaneous spectrum instead of a fixed spectrum. To get heterogeneous, non-homogeneous stationary noise, you can rely on POD or EOF strategy, which means that you need to have some fine resolution simulation of your deterministic system. You take the snapshot, you then apply SVD to diagonalize the autocorrelation matrix, and then you use the eigenfunction of this tensor in order to build the basis. So the basis will be fixed for all time, so that's stationary in time. You can split this basis in order to represent the resolved velocity and keep some basis function to describe the noise. Okay, and the noise are weighted by the eigenvalues of the autocorrelation matrix. So you can go now to non-homogeneous, non-stationary noise by nearly sticking to the same kind of principle. You can build pseudo-observation of the velocity fluctuation, then again use the autocorrelation matrix of this observation, and then get an instantaneous basis to describe the noise. Of course, this is at the price of doing this SVD at every time, so it's quite costly. But here you don't need data. You don't need the high-resolution simulation to build this noise. It's based on the current simulation with some scale similarity assumption. The other way to go from POD stationary noise to a non-stationary noise consists to slave the basis on the first POD mode. So it means that you have to project the fluctuation, the velocity fluctuation on the first mode to select the corresponding to the value of the coefficient of this projection. You can select a series of events in the phase space that corresponds to the value of this coefficient, and then correct the by the empirical variance the coefficient of your noise decomposition. So in that way, you have slaved the basis to the first mode values. So I will describe two kind of results. So the first one is on a double periodic domain for the barotropic QG equation, and the other one is on a square box with wind forcing. So the first experiment is okay, our BQG system initialized by a monochromatic Rossby waves. So in the deterministic setting, this monochromatic wave is a solution of our system, so it stays stationary. But if you inject in the system a stationary noise, then you still have these Rossby waves. They are preserved, but you see the superimposed here the effect of this homogeneous noise. But it does not destroy, and that's a good news, it does not destroy the Rossby wave. If you use now non-homogeneous noise, which is based on the pseudo-observation of the velocity fluctuation, then you can see that the noise triggers some secondary circulation. So, and this is because of the modified advection, indeed. So it plays the very same role as the Stokes drift in ocean modeling, and in fact we can show that this location uncertainty modeling embeds in it the Craig-Lebovich system that describe the mean current wave interactions. But still, it conserves the Rossby waves. So for the second experiment, so we consider now always our BQG system, but now on a square box, and you have wind forcing with westward and eastward winds that's an idealization of the North Atlantic circulation. And if you let run the system for a sufficient long time, then you can see a stationary distribution emerging, in which you have here the average of the stream function. You see two central vortices and two external vortices that represent boundary current in this square box. So we will compare what we call a DNS simulation, which is 256 by 512 resolution, LES simulation that has been finely tuned, okay, to get the best results, but this is on a very coarse grid, and the stochastic simulation with three different non-homogeneous, non-stationary noises, or stationary and non-stationary noises. All the model, all the coarse model, they have the same subgrid diffusion term. So they have exactly the same coefficient as the LES simulation. And so we can compare the root mean square error of the different moments, so the mean, the variance, the skewness, and the kurtosis of the stream function, the potential vorticity. For the variance, it's the velocity and the potential vorticity. For the skewness, the stream function, and the same for the kurtosis. And so as you can see, the stochastic models, they always improve the results of the LES simulation. Okay, and so as you can see, the best improvement is obtained when you inject data, okay, through the pod basis, so meaning that you inject some information of the high resolution simulation, and it's non-stationary in time, so you inject some kind of dynamics for the evolution of the noise. Here there is data, but it's stationary in time, so no dynamics for the noise. And here it's, there is no data, but it's non-stationary, and it's based on the velocity fluctuation of the current simulation. So it's a good alternative, this one, if you don't want to inject the data of a high-resolution simulation. So these are examples of the solution we obtained. So for this is the reference one, the stochastic average of the stream function, the average you obtain for the LES solution, the same for the potential vorticity. So as you can see, for the LES, the solution is much too smooth. So for the eddy kinetic energy, the same, okay, the eddy potential entropy. The skewness, so you see two large rare events for the LES solution, and the same for the potential vorticity. For the kurtosis, we see also two strong rare events for the due to the excessive viscosity of this solution, and it's improved by the stochastic modeling. We can check that we have grid convergence. So now if you refine the grid, then you converge to the truth, okay? And then it goes quite fast because even with 32 by 64 resolution, and you have something that is quite close to the reference. And that's the same for the kurtosis or the skewness. Okay, so in conclusion, this stochastic setting allows you to construct better LES or coarse model for geophysical flows. It captures better the long-term statistics that you are looking for, and it offers also an additional degree of freedom with the injection of this noise. So you can discuss it in the scaling of your equation and obtain a variety of model with this, depending on whether you put a high noise or a low noise. All these will be continued. So I'm very happy to advertise a project we have with Bertrand Chaperon from Ifremer, Dan Krizan, Daryl Ohm, and myself on the study of stochastic transport for upper ocean dynamics. So the main goal of the project will be to specify the noise from high resolution data to do data assimilation, data analysis with this stochastic transport tool, to do some mathematical and physical analysis of these equations, to design specific numerical schemes for this stochastic transport, and to build some fine particle filter strategies based on this idea of stochastic transport. Thank you very much.
Okay. Michael?
Thank you very much. The test that you had at the end, where, if I understand correctly, on this wind-driven double gyre problem, but only on the fixed points, I mean stationary solutions, I didn't see.
Yeah, okay, the goal was to compare the stationary distribution you have for the high resolution simulation and the one that we obtained from the coarse simulations.
I understand that, but it didn't look very interesting oceanographically. I mean, how, you only tested the performance at the base, essentially the root of the bifurcation tree. So what happens in things that look more like real oceanic flow?
I think he's looking at the distribution, right? Or
well, it still, it can, I understand, but it...
Yeah, okay.
It didn't look like anything I'm used to see.
Yeah, okay. The goal of this work was to show that for a traditional diffusive setting, such as you have in the some LES strategy, then you have wrong statistics of this. So if you're using classical subgrid model, then you won't have the good statistics of your solution. The long-term statistics,
I think there's a misunderstanding here. So I think what you've been doing, high-resolution models.
yes,
All kinds of eddies and stuff, right?
yes,
Exactly. And he's comparing the statistics of that high-resolution model with the statistics of the stochastic model. So
exactly.
I don't think it's the beginning of the bifurcation tree. He's
No.
using highly determined simulations to show the distribution.
Yeah, exactly. Yeah. It's correct. Yeah, we can discuss about that later.
Any other question? last question? Okay, so if not, thank you very much, Étienne.